Okay, guys, what do we use subroutines for? Anybody got any comments there?
It's a way to get the program without have to search search the whole program.
Well, obtains additional life.
Well, what it does is it allows us to take extremely long programs and break them down into modules.
Right.
And then also it allows us to share subroutines between other applications. Does that make sense? Well, that means I might have 5 different stations and all of them have the same each stop circuit. Well, instead of me having to reprogram all that permissive circuits, sometimes on an each stop circuit on a big line, you've got really a lot of buttons. And if I had to go into every PLC that I've got, and reprogram that each stop circuit in there, that's going to take a long time, right? But if I save it as a subroutine, and then go over and import it into my next application, right? You understand? Then I can do what? Oh, well, but you save all that programming. So if I've got a section of a PLC program and I've got all these PLCs that use the same circuit, right? And the eStop is a perfect example. Then what can I do? Well, I can create it as a subroutine and just do what? Yeah, just upload it into the other machine or bring it in off my hard drive or off a USB drive, right? Understand that into that program and just insert it in there. But the main function of subroutines is we can take an extremely long PLC program and we can break it down into submodules. But each submodule having a specific function, right? You understand that? And now instead of me trying to find a rung in 3,000 rungs of code, instead of me trying to find that code that handles this, all I have to do is just go to the what? So to a subroutine.
You said a way to take a long program and
Break it down into modules.
break it down into modules.
This is what they usually refer to as structured programming, by the way. Because the longer a program gets, and you already been seen it in these programs that we're writing, which are fairly short, where you have problems finding certain things in there, right? You understand? We got nine rungs. Like I say, which rung does this, and you have to go back through that thing and you have to find it, right? You understand that? Oops. I don't know if I downloaded it or not. I need to hook my PLC up. So on Allen Bradley, or the 500 programming language, is we can have up to 256 subroutines inside a single program. And this is the RS Logix 500 program. We look at conditional, sort of like the jump instruction. We can make it unconditional or we can make it conditional. Now, how do we make it conditional?
Make it conditional. We have to insert some have to be.
Yeah, use the compare instruction. Yeah. On the input.
True.
Yeah.
I want this to
To use compare instructions in the main PLC ladder diagram to call a subroutine. So when we run a subroutine, they're calling it a call sub.
Say it again.
So when our program says, okay, we're going to run this subroutine, they usually call that a call subroutine. That's the terminology. And then, of course, in this section, we're going to also look at interrupts. So it says specific subroutines can be called. So when we do a jump instruction, we can have conditional or unconditional jumps. But we jump inside a program, right, or inside a ladder. What we do with subroutines is we call another ladder, right? Understand? Completely separate. So jumps, we changed the flow of the scan with inside a single program, right? You understand that? Jump to subroutines is when we call another ladder. Jump to another program.
So it's not, okay, so it's not contained.
It's not contained within the main program. RS Logic, RS Pro, and that's what I'll look at my PLC the next break, and we'll look at how we can set one up. But in RS Logics, it comes with a certain number of subroutines built into it, and it should open when you open RS Logics. So it's already running, Rich. Yeah. So when we look at our project window, which is so what we have is we have ladder 2, Allen Bradley calls ladder 2. I'm on the project. Allen Bradley calls it ladder 2. That's your main data file for the actual ladder logic, right? That makes sense. What is Siemens called there? QV1. Okay, that's what they call it. So QV1 on Siemens is exactly the same as what ladder 2 on Allen Bradley. And I'll have to still figure out how to do subroutines. RS Logics has has 1, 2, 3, 4, 5, 6, 7 subroutines built into it. So what happens is as you add subroutines, what's going to happen is that down at the bottom, if I can get my taskbar to disappear. What happens is you get a new tab at the bottom with the subroutine that you create. And then what you do, you go to that tab, and then you build a ladder for that one, for that subroutine. Like I said, RS Logics, on Logic Pro, you've only got this menu right here built into it. I don't think you can add some more. You might play around with that if you want to. But this should come up automatically. On ours, all we should see right now is a ladder 2. But every time we add a subroutine, we're going to get another tab on the bottom. And we'll also get a listing up under the program. Okay?
They were real handy because you can leave those tabs open, and then time you need to go to them, you get that tab.
Select the tab, yeah, I really do. And then plus, they're called them SD subroutines. You can give every one of your subroutines a name. So what you do is you give it a name basically on what it does, right? You know what I'm saying? So what happens is that when you want to go, okay, I want to see what's going on with this ripper out there, you can do color the tab that controls that. Very easy to make a list, real easy list that you can write down comments about a subroutine, and it would make them easy to go through. I don't know if I've got anything open on the Logic Pro. I mean, I'm sorry, got it down here. Let's see if it brings in the last subroutine. I think it does. Let's see if I saved it. No, this is the one I'm working on RPM, but I'll have to figure out where I did it. I'll look up PLC and look at some of the Festo PLC programs, and then show you all that. Are we okay?
If you jump, no, man.
Go ahead.
I was just a small question. If you jump to it, it starts that program, that routine, but it don't. It still go back and start.
Well, only if you tell it to. So normally when we put a jump subroutine, subroutine is not intended to be a standalone program, right? I mean, it can be. But, so what we do, on this guy, different programming languages do it a little different. This guy is pretty much, well, what I learned in programming. So what we do is we assign a subroutine a name. And then what we do is we jump to that subroutine, right? Everything. Then what we do at the end of the subroutine is an instruction, we call it return. Now, what would happen if we drew this as a block? Oops. Where's my PowerPoint at? I closed out my blanket. Let me just, so basically what we would have is we would have a main flow. And then we might do some stuff in here, right? And down here we might have, we'll just put a JSR. And then we would point it to a subroutine. Well, this subroutine is over here. But what would happen is the very last instruction, we'll just put RTS with the return from subroutine. So what this would cause to happen is this would cause it to go here. It would come down and run this, and it's not scanning this program over here. And then what would it do? To the next ladder after the, it'll be your next ladder rung after the JSR. But down here later on, I might want to do what? I might JSR to the same subroutine. And then it would come up here, and it would run through the subroutine again, but this time it's going to do what? It's going to go back to the next rung, the next rung after the JSR. It'll always come back to the rung under the jump subroutine. So you can use the same subroutine over and over and over again, and that's what's neat about it. In the old days of programming, before they came up with this, you had to literally repeat the rung. Every time you wanted to do the same thing, you wanted to repeat the rung. Of course, these are computers, and computers have been able to do JSRs as long as I've been programming computers. There's always been a jump subroutine. Which means now, instead of me having to repeat all those lines of code or all those runs, I can just do them once, and every time I need them, just do what? Yeah, just jump out. And it will always come back to the next rung after the what? After the jump instruction. Jump subroutine. So it automatically remembers what it is. It uses something called a stack, which we'll talk about later.
Rich, that RTS stands for
Return subroutine. Now return from. RTS is return from subroutine.
That's okay, it is returned.
It's just an abbreviation. That's back in the old machine language programming days when you were programming. And when you looked it up on the instruction set, that's what they called it, RTS. Return from subroutine. So this is what they're showing here, in the book. I don't know which figure this is. Subroutine number 1 and subroutine number 2 are called from the main program. And what it does, it automatically, so here we'd say a call subroutine, JSR call. And then they would do what? They would send it down to the subroutine. At the very end, we have a what instruction? Return. And it would bring it back to the rung under the call, sort of see. Okay. So it goes to the next rung. We don't do the JSR again. So we have something called a stack that holds the address of the next instruction to the going to execute. So when they say next instruction, here we're talking about the next rung, right? After executing instruction in the subroutine, a return instruction at the end of the subroutine causes the program to counter to return to the main program. And these guys are really, really good. Saves you a lot of headaches, splits your program up instead of going in and trying to figure out. So the robot we have over there that's operating the Amatrol line, that program is pretty long. Right, you understand? So what did they do? They split up subroutine, which is really neat because for some reason when the guys set the line up on one side of the room, we moved it over to the other side of the room and the robot messed all the points. So instead of me trying to go through the whole dang program and find where those points were, what could I do? I could just go to the subroutine and keep going through the subroutine until I got the subroutine running the way I wanted it to. And then I would go to the next one and the next one, which is really what it needs. So I made reteaching all those points on that robot program extremely easy.
So, okay, so when you ran through the subroutine and you got it where you wanted, then you just teach it.
Yeah, and we just retaught that one point. And then what was nice is that about subroutines is you can run them without, right? In other words, if you don't call them, if you just run them, then they won't leave the subroutine because there was no return address saved. Does that make sense? So what you can do on the PLC is you can just go through the same section until you get what? Until you get all the bugs out of the subroutine instead of trying to go all the way and find it inside a section of the PLC program. And this is why we call this structured programming. When we break these large programs into individual little sub-modules, and then what I can do is I can play around with a sub-module without affecting anything else. Okay,
First, the program counter is the stack.
no, the program counter is what we change. Okay. So this would be like, you're reading a book and you want to go somewhere else. What do? So you got a page number. That would be like your program counter. But when you're reading a book, you can go to any page you want to. You can go forward, you can go backwards. But how do you keep up with where you were at? Well, you either stick your hand in there or you turn it, you tag it, right? You understand that? Well, that's what the stack does. The stack is not the program counter. The program counter is what's actually counting through the program. So we're going 1, 2, 3, 4, 5, 6, 7, 8. And I'm fixing to leave this guy and go over here. Well, what we need to do is we need to save our program counter where we're at. So what it does is it automatically pushes that on a register called stack. That's the return address. It's called last in, first out. It's called a LIFO stack. So what happens when it sees that return, it pulls that last address off the wall. The stack. Sends it right back. So it's just like you tabbing your book, right? You understand, or making little notes on how to find your way back. So it's really, really good. And the stack comes into play on indexed addressing too. So a stack is just a temporary storage location that the program can automatically use without you telling where to put it. You don't have to tell where to put it. You don't have to tell where it comes from. So the stack is set up automatically every time you start the thing up. And we call it pushing. Pushing is the instructions in machine language is a push and a pop. So if we want to manually get information off the stack, we pop it. If we want to push information on it, we push it. Or when you do a jump subroutine, it automatically pushes and pops it. But it's what we call a LIFO stack. What does it stand for? Last in, first out. It just works exactly like.
Push instructions on top of the stack.
And pop them off. So for some reason they didn't say pull, they call the term came out to pop. What it uses in here, we'd have to look. I'm back in my old machine language programming days. So when these computers first came out, there was really no high level languages. So we had to program the computer on a binary level, which was. Did you take microprocessor class? Prior to jumping to the stack, here it is right here. Prior to jumping to the subroutine module, PLC processor creates a stack. Actually, it's created right off the bat. What we do is it saves the return address on the stack, goes out there and runs the subroutine, and then it does what? It pulls the return information off the stack. And this is something we can access the stack. It's got later on we'll learn where it's addressed at. You can access it. You can push stuff on it. You can pop stuff off of it, and it's really neat. It's one instruction. You don't have to specify. Once you set up where the stack's at, you don't have to specify addresses anymore. You just do what we call a pull or a pop instruction. I don't know what this here. Pose the contents of the following registers. So it saves your program counter, changes your flag register, and any general purpose register or pointers. And then we call the subroutine, which I'll call the JSR, that's just the way I learned it. The processor causes the processor to create the stack, starts executing instructions in the subroutine, and how does it know where to come back to?
Return.
Well,
Yeah, I think this is probably wrong. The book don't really, the stack is already there, right? You understand? And what this does is it causes the information to push all this stuff on the stack. Everything that was going on with the instruction, program counter, the flag register. Because it might have to use these same registers when inside the subroutine, right? Does that make sense? Pulls the contents of the memory out of the stack when it hits the return instruction, places the contents back into the processor register, and then starts executing the main program. Here we're dealing with ladder logic. So what happens is the last instruction that it was occurred before the JSR, it saves everything that was going on. So if it's a math instruction, what would it have to say? They have to save all your accumulators, right? Your source A, source B, all the general purpose registers, all your flag registers. Know if it had an overflow or whatever that. Pushes that onto the stack. And then it goes out and runs subroutine. Well, when it runs the subroutine, it's going to use those same registers, right? You understand? It's going to use the flag register, might use accumulators, might use, anything else that's capable. And then when it gets through there, then what does it do? It pulls all the old information off. So what that means, if you got something in if you got something in a subroutine that was affected by the previous instruction, then you better save that so you can access it from the main program. Does that make sense? Of course, we can save everything. Of course, if you use different timers and stuff, of course you needed to do that. Where a normally open switch, which one's closed. So this must be referencing an actual diagram inside the book, which would be this guy. So on jump instructions, we use register what? Q. Or Q. Now on those jumps, remember that. I don't have my textbook out here. Oh, I'm saying Q. It's actually out. I got to watch my thing. I'm still trying to learn the Siemens PLC.
Label.
Now jump takes us to a label. Oops. Just jump something. Yeah, but this is what we're trying to look at. So your jump instructions use it is Q. It is Q2, right?
Yeah.
So we use a Q2 register to specify a jump. And then we have to jump to a label instruction that has the same address. So JSRs use Q2. Right, okay. Yes or no? So we can literally have how many jump instructions? We have 256 inside the ladder, right? But I'd have to look at that. Now subroutines use U. Oh, this is still messed. Let's see, let me find it. So where am I at? So this is unconditional jumps. Oh, here we go. Here it is. So JSRs use what? U. So jumps use Q2, JSRs use U. We specify a number. Everybody okay? Yeah, so each subroutine has, if you want to call the same subroutine ladder, we would use the same U number. Right? Everybody understand that? So here we're calling two different subroutines. So what would happen is on this guy, switch 0 is, so it'd be sitting here standing. If neither one of those switches were closed, then it's going to just go over these, right? Still going to scan the input, but it's not going to update the output. If I close switch 0, then it's going to go to subroutine U3. If I close switch 1, it's going to go to subroutine U4. Everybody okay?
Yeah.
Yes or no?
Oh.
Nice little note to make. So what we do to create this is we go over here, and I'm not sure if you right click or not, we'll have to look at that, but you go to program files, and then one of the things I have at the very top is what? New. So we click on that new, we're going to create a what? A subroutine. And you're going to have to probably specify a name, right? Like I said, after we take our break, I'll bring this up and we'll go through it to make sure. So here they're giving it a subroutine. So here they're naming it sub1. But you can put anything you want to in it, right? A number, this would be your U number that you're making. So over there, if you put a jump subroutine U:3, and the first thing you have to do is specify the number, right? You understand that? Then what do?
Right, and what number
This is
sub?
required. So the first two are required. I'm pretty sure this right here is optional. Then when you do that, you're going to do what? Click on OK. So subroutines must have a subroutine instruction. Is it called SPU? Let me go back and look. No, it's called JSR. At the beginning of the program to indicate that this, oh, I'm sorry. This is the actual return. This is actually the subroutine. So the subroutine must have an SVR instruction at the beginning of the program to indicate that it is a what? Subroutine. And then the very last rung before the end, when we say the very last rung, that's the program, that's the rung that we don't specify. Anytime we create a program, it automatically puts an end instruction at the bottom, right? Then the last instruction in the subroutine should be a return. Are we okay? Okay, so far. And most industrial applications, linked ladder logic diagrams are required for the PLC. Like I said, we're doing very small programs, but you got to understand, you get out here and you get a PLC that's running a sure enough production line. There's not going to be any 9-line runs, right? Unless it's a subroutine. 9-run program. So what we need to do is we need to be able to understand we can take that large ladder diagram and divide it into several modules or subroutines. Now all of a sudden it makes it a lot easier to manage that program. I mean, a lot easier. So normally if we look at the Festo, as soon as I download it, the main module is primarily just JSR. JSR. So that's what they do. That's very, very normal. So you have a main loop that's basically nothing but one. Jump subroutines, and then you go out and build your subroutines individually. And if we have different programs or different PLCs that needs the same conditions, then what can we do? we can use that subroutine inside that PLC too, right? Mr. President? Subroutine application, so this right here is this is called a subroutine. So this is pretty standard. So over here they're using a counter depending on the count. So these are what we call conditional subroutines. So when we start combining the JSR instruction or output with a compare input, right? You understand that? Then now we can determine when the subroutine is actually called. If it's on a line without an input, then it's going to call that subroutine every time through the scanning. We okay?
If it's on the line,
Yeah, without an input. I mean, we do that all the time, especially if we're going to just call subroutines. So what we're saying is, if I came up here and did what? Did not have a contact in it at all. It's just a straight piece of wire. This would be what we call an unconditional JSR, which means no matter what, every time it scans, it's going to go off that subroutine. So most of your main modules is written like this. I mean, they just have a bunch of JSRs, right? You understand that. And when it starts scanning, it goes out, runs this subroutine, goes out, runs that subroutine, goes out, runs that subroutine. And then when it gets back to the bottom, what does it do? Yeah, just scans through this. So a lot of your structured programs are written, you have what we call a main module or a main program. And I'm not saying the only thing it does. You know, your e-stop circuit might be in the main module. We wouldn't have that in every sub.
I thought you said after, okay, that's an unconditional sub. It's gonna run.
The book calls it a switch. If you put a switch in there, for some reason they're calling this unconditional, but that's not true. Because if it was unconditional, the switch still has to be closed.
At the end, when you get that return to subroutine, I thought it would have jumped down to ladder 2 after it completes both of those subroutines.
No. Why would it jump to ladder? This is ladder 2.
I mean, run,
Well, once it jumps to this subroutine, it would go out and run the subroutine when it sees the. So this came out of ladder 0. This came off of run 0.
right,
Okay, so where's it gonna come back to?
run 1.
Run 1.
And after it does everything what it says in that one, then
It's gonna come back to
hopefully to 2.
2.
That's what I'm saying.
Supposedly it is. It come back to 2, and it hits the end. What would it automatically do when it hits the end? Go back to 0.
Because we don't have to toggle it.
Well, this is the end instruction. The end of a ladder, you don't put any decision making in the end. It just tells the computer that that's the end of this scan cycle, and what does it need to do? Yeah. So what does a PLC do? What is that PLC doing? All the time. Yeah. Normally, if it had nothing to do, it would just scan like this constantly. Okay. But what we're doing here in ladder 0, we're sending it off to a subroutine, and that subroutine comes flying down through here, and then the last one is a what? Return, and they're calling it RET. Where would it come back to? Well, it's going to come back to that right there. Yeah, and then it's going to do what? Well, it's going to go out here and run a different subroutine, which is somewhere out here, right? Okay, then this is going to be an RTE. So this guy's going to call this guy. It's going to run it. It sees the return. Where's it going to come back to? Line 2. Line 2 tells it to do what? Scan, it'll start, yeah, and then it'll just redo the scan.
When I look at the book, it shows the return, but there's no address on the return.
Well, the problem is, all the return does is a subroutine, we don't want to specify where it goes back to. Because it's going to go back to right after. So see, that was pushed onto the stack. So that would be very confusing if I could bring my subroutine back from a different spot that I came from. So JSRs will always do what? Well, that's not true. Once you find the address, once you know where the stack's at, you can change the return address. But that's the only way you can do it, is change the contents of the stack. And right now, we don't have control of the stack, right? But we can't specify where it goes back to. What it's going to do is going to pull all that information off the wall, off the stack. So no, the return does not have to specify, that's a good question. Any more? Okay, guys, y'all go ahead and take a break and I'll bring my pen. And we've already looked at this, we're okay? So these would be conditional jumps, JSRs from subroutine. So the first one would only go out to subroutine U3 when what?
When the accumulator counter equals 10.
Yeah, when accumulator encounter 0 is equal to P. The next subroutine would only execute, oh sorry, I'm going to that. The next subroutine would execute when,
When A is less
yeah, on A, accumulator encounter 0 is less than 10. And this right here would go to this subroutine.
than accumulator greater than
Right. So this guy here would have three subroutines. That's so what figure is this?
12, 1. Yeah, so.
Darn it.
We gotta have both of them. South of 12, 150,
Yeah, we'll see. So this is 12 what?
12, 7.
Through 8, 9, 10. So that's all our subroutines. So this should pull it in right here. Are we okay? So when we look, of course, these tabs are going to pop up here, but here's subroutine. So this is subroutine 3, right? This is 4, and this is 5. Are we okay? And then this is ladder 2. So let's see, we got everything?
Download.
Not yet, I'm looking. So, and I don't know why my taskbar is not disappearing. It's supposed to disappear. Okay. So this is subroutine 1. So this is the one we just got through looking at. Sorry, this is ladder 2. Here's subroutine 3. So notice the first instruction is SBR, which identifies this as a subroutine. Then it looks like it's got no decision in this, so it looks like if we run this subroutine, then output 2, 0, and 2, 1 should turn on.
Without input?
Yeah, you don't need inputs. If you don't want something to be conditional, but this is kind of conditional because they won't do it unless the subroutine is running, right? You understand? Okay, you understand that? Are we okay? So when subroutine runs, these should come on, right? You understand? Now the next subroutine, which is subroutine, what they're calling 4, y'all keep up with these lights for me.
Sure.
So the first one is 0 and 1. This is output 2 right here. So the first subroutine, ladder 3 or subroutine 3 is 0, 1. Then the next subroutine, which is subroutine 4, is 2 and what? 2 and 3. And then the next subroutine should be the next 2, I guess, is 4 and 5. We should go right down the line, right? So, huh?
So the thing 4 is just wrong too. Oh,
I'm talking about, I'm looking up here. This is the program. Let's don't look at the book. Let's look at this. Yeah, so this subroutine right here, if this subroutine runs, then 0 and 1 should turn on. Okay. If subroutine 4 runs, then 2 and 3 should turn on. And then if subroutine 5 runs, then 4 and 5 should. Now these might have been modified from y'all's book to make it work like that. So, okay, so let's go back to the main ladder, and then we'll upload it, and then we'll run it.
So it's already going to subroutine 4
Yeah, because why?
because it's less than 10.
Yeah, so it says if this is less than 10, then do what?
So it's subroutine 4.
Okay, so let's start counting our counter. So that's 1, 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, why didn't the other two turn off?
Because you haven't got to.
Because we're not scanning. There's nothing to turn them off, right? You understand? So the first scan, they were turned on.
because it was less.
Yeah, but so what happens now is that we don't have anything that would do turn them off. So all these are going to stay on. So let's go on. I'm going to come up here. So this would be 11, 12. Okay. And then now all 4 of them's on. Right? And then 1 is a reset. Now, of course, we're not proving much because once we got them turned on, why?
Because we did reset stuff.
Yeah, there's nothing to turn the outputs off. Once we run the subroutine, right, you understand that, and they're on, then they're basically gonna stay on in this application right here. Unless we go into the subroutine and do something wrong to turn them off. So we could do something like this. So we'll put another set of buttons in here to actually turn them off. So we'll call this like input 14. And we'll call this input 15. And then we'll call this, we hadn't used any bit register.
Well, they're using subroutines.
There's no bit registers using subroutines that I saw.
Did not put a load in the subroutine first.
But their output, I don't know, thank you, Larry. Well, we'll see what they're using over here. No, they're actually using outputs because it's turning on lights.
Up top, what that is no other.
Okay, so I can't use V3. I can't use it. Let's see what they use on every one of them. They probably use 1, 2. And so we can use 4, right? Oops. Thank you. No, I wasn't on ladder 2. Okay, so we need to change this switch right here to a normal close. In fact, I didn't put a slash down there, so this is the kind of little problems that you run into on Logic Pro. The check valve, and I wrote programs before, and you can't look at all situations. But I specified a 16-bit word for a contact. RS Logic would have probably gave us an error on there. So I'm using 0/5. So RS Logic Logic Pro is a really good application, but it's still got some problems. Okay, does that look okay?
You have to fix
Yeah,
one.
How's it gonna stop?
Two different addresses.
Unless you use the,
Does that have a slash on the physical output?
Yeah, this has 3.5, and this is bit 5.
Okay, I thought you slashed
I did. They're supposed to be slashed. This one wasn't slashed.
what I'm saying,
The last one slashed, the output actually slashed?
Yeah. 0/5. I know it's small, guys. Yeah, so this 0/5, and this is, so it should work.
What's gonna work?
Well, what we're gonna do, wait, I know what you're talking about. It ain't gonna do nothing, is it? It ain't gonna do nothing.
Ain't gonna stop that.
So what we need to do is go into our subroutines and add that bit. Yeah, we're using a different contact. We're controlling this from another. We'll see if it works. Hopefully it does. Yeah, so I think I got them all. Okay, it's ladder 2, got it in run, right? Counter's counting, nothing's happening. Why? Which is what we expected.
You close that bit up there.
Yeah, I know, that's what I said. Okay, go ahead.
Still got it open.
Yeah, so we'll come up, what we're gonna do is come up here and seal it in. Okay. Now the 2 outputs came on that we expected, because this 17 is true. Right? And then I'm gonna come up here and start counting. Okay, so yeah, these are still on because I turn all of them off now, right? Okay, so let's see what happens when we come up here and do this. Okay. Yeah, so now the only 2 that's activated. Okay. So we'll go up here and go, so this would be 11, 12.
It's not giving output. The output is cell open.
Yeah, I didn't, yeah, I thought I did that, yeah.
Now you get this.
So then I do this one, the 2 that's not true is going to go off, right? Understand? So what we did is we added a sealing circuit or a memory circuit or a 3-wire circuit, whichever one you want to call it, they're all correct. And then I put one of the contacts off of the 0/5, I put that in every subroutine. So that means if I come up here and reset the counter, which is 1, okay, and then what can I do? Then I can come down and hit this, and basically it should. Now this one's still true. So what it does is it turns off the 1.1. So before we had it before, the only way you could have got that back is to restart the program. I might leave that in there. I might say that. It makes it a little different. But what's nice about subroutines, so these are all what we call conditional JSRs, right? So conditional JSRs, we usually combine them with a compare instruction that only determines when the subroutine is executed. And then every subroutine has to start with what?
Say again.
Every subroutine has to start with a CR, right? With the subroutine name. Then every one of them has to end with a, yeah, and unfortunately the JSR is considered to be an input instruction. And if you put an input instruction on run, you gotta have a what? You gotta have an output. So here what you probably need to do is use one of the bit registers. Logic Pro only supports B3, but I think both the 504s and the 1000, the MicroLogic 1000, I think they support B3 and B3. So you actually got 512 bits that you can deal with to use it, what we refer to as internal contact or internal coils. And you get people new into PLCs, they think they've always got to use a what? They think they always got to use an output. Now they think you got to have an output over there. But if that contact if those contacts are not don't need to generate an output, then you need to get used to using your B3s and what's the other? B10. Some even support more. I mean, that you can actually do. So subroutines. Let's see what else is in the PowerPoint before we move on. Make sure we clear everything there. Oh yeah, interrupts. Just look at mine, the ones I have that they have, these are actually the ones that came from the book. So. Nested subroutines. What are you thinking nested subroutines?
One inside subroutine.
Well, that's when a subroutine calls a
Subroutine calls the subroutine.
Right. Y'all understand that? Is this in the book? Y'all going through the... Well, we need to talk about this then. Because this is something we do quite often. And what happens is it always saves the path back. So this would be like I have my main program and come over here, right, coming down through my ladder. And then down here I have a JSR, and let's put like 3. And then we'll come on down here. And then I come over here, I have a subroutine. What's it, SBR is what they call it? And this is 3. And then of course it's going to start coming down this, right? Now eventually what it's going to see down here at the bottom is an RET or return. Are you okay? Okay, but what about in here if I said SBR4? So I've got another subroutine over here. And I'm just gonna put the S4. Now what does this guy end with? Yeah, return. So what's gonna happen, it's gonna come down through here. Now this is a subroutine. But we have call in another subroutine. Well, when this guy here sees this return, where's it gonna go back to? It's gonna come back right here. Now when it comes down to here, where's it gonna go back to? Yeah, right there. And we call these nested subroutines. So a nested subroutine is when we have what?
Subroutine within.
A subroutine within a subroutine.
So that's not like the interrupt, what they call it?
No, we're not.
interrupt?
No, interrupts are completely different. Interrupts are hardware generated.
So, that SBR4 is right there, you will not use JSR.
Yeah, thank you. I was giving it a name instead of that, but thank you. Yes, you would. And then, of course, inside here, I could have a what? I could have a JSR 5. And then over here, I got a subroutine called 5. And then it's got rungs in it. But every one of them's going to end with a what? Return. What do you mean? Yeah, so my main program, so this is my main program. So this guy here is gonna, what's the last instruction here that we don't generate is gonna be an end. So this is our main. So this guy here would be doing what? Yeah, it'd be looking.
Looking for activity.
Right. So if there's a JSR 5, 3, it's going to come up here and run this subroutine. This says jump subroutine 4. This is going to jump to subroutine 4. This says jump to subroutine 5. This says go to 5. Down here it says return. Well, what it's going to do is it's going to go back to the subroutine that called it. So this will come back to here. And instantly it would do what? Return to here, it would run this rung, and then this would return back to the main program, and then the program would scan it here. We call these nested subroutines.
The message your line from JSR3 to
My bad, where?
subroutine 3. Did you leave that line?
Oh,
Show
yeah.
that you going up.
Yeah, thank you. Yeah, you're right. And we call these guys what?
Nested
Nested subroutine. And what is a nested subroutine?
Subroutine within
It
a
calls a what? Subroutine. And that's what's so neat about that stack. It's a last in, first out. So every time it sees the JSR, it pushes the return information on the stack. Then the next one, it pushes the return information on the stack. The next one, it pushes the return information on the stack. And then when it says that first RTI, it doesn't pull everything, it pulls the top of the stack, right? I'm saying. And then when it gets the next one, it pulls the top of the stack. Now later on, when we look at this, we have the ability to change the stack. Normally we don't do that. But if I know where the stack's at, what can I do? Now we can change it. Yeah, we could adjust the stack pointer. We could change it. We could change. It's nothing but memory. It's read-write memory, which means what? Oh yeah, it means you can change it. So we could change the return. We could make a program that changes the return address if we wanted to. You know, but right now we're not doing it. I don't know. Something we don't do. Something in microprocessors. We have an application where we deliberately went in there.
So you saying a nested subroutine, the whole answer, it would be when a subroutine calls another?
Calls another
Another
subroutine.
subroutine. So we wouldn't say subroutine within a subroutine that calls another subroutine.
Well, that's not, this subroutine is not within that subroutine. So JSR, that is not a subroutine within a subroutine. Understand what I'm saying? So it's when a subroutine calls another subroutine. Those two subroutines are not in the same ladder, right? You understand that? This is what you were saying. I'm sure you knew what you meant, but the way you said it was wrong. So you said a subroutine within a subroutine. That is not a subroutine within a subroutine. It's a jump subroutine structure. These are what we call nested subroutines. And you're gonna run into this. It's not desirable because it starts getting, but you're gonna run into it. And what I found out a long time ago, if something's available to an engineer, they're gonna use it. Are we okay? Yes or no? Interrupts. So normally what the PLC does is it scans, right? You understand? Right? Okay. What if an input changes after it's been scanned?
Stop. Off.
But what if, I'm asking now, right now, what would happen? This would be like me up here, and I don't let y'all say a word. Don't let y'all say a word. But every once in a while I say, does anybody have any questions? All right, you understand? But a scan would be like me going to everybody in class, like I said, you have a question, you have a question, you have a question, you have a question, you have a question. And if I wasn't at that point in the scan, then you couldn't ask a question until I did what? Until I went back and scanned, started my scan. So what we said, we used to have this problem all the time, especially on extremely long inputs, extremely long programs where we have a high speed input that the PLC just missed. Because it happened between scans, right? You understand that? So the input changed states and went back to its default state between scans. Now that would be awful if it was like counting my number of production pieces or stuff like that, right? You understand? And I had to depend on the speed these things was flying by. So normally what we do in a class is that we don't do it this way, but in a formal classroom environment, what I would do is every once in a while, I said, if anybody had any questions, of course, we're not going to let each one of y'all, but if you had a question, you would do what? You'd raise your hand. And that would be very similar to what we call an interrupt. And when you raise my hand, no matter where I'm scanning over here, I might be over at Noah, right? You understand? Now, but Tim raises his hand. Well, what would I do now? I would come back and service Tim. So when we got extremely high priority devices, input devices, that needs to get the attention of the processor, no matter where it's at in the scan cycle, we're going to use what? Interrupt. Interrupt scans of the main program ladder logic, similar to subroutines, must reside in ladder 3 through ladder 255, which is, so the subroutine, we call these interrupt subroutines. And of course, you don't put an interrupt subroutine, they're going to be a subroutine. So if it's a subroutine is not in ladder 2, right? It's got to be in ladder 3 through 255 for our logics. Now you might get into a different PLC that has more as well. What determines exactly how many subroutines you can have in a program? How much memory the PLC has. So that's something when you get a PLC, or when you get at the book and look into it and see this. So. INT instruction identifies that the routine is an interrupt subroutine instead of a regular subroutine. So we have an INT instruction. Now let's see if RS Logic supports that. What group would it be in?
Program.
Yeah, program control.
Is the AFI in the program control?
in the RS Logic, just because it's not here, so RS Logic, when the guy that wrote this, he didn't support, looked like he didn't support, let's see, let's look at other stuff. These are file, this is ASCII, and of course RS Logic Pro doesn't support any of these. Y'all did learn ASCII, right? So this has no trig functions in it. RS Logic has no, RS Logic Pro has none of those. So let's see what we got here. This has a high-speed counter in it. What's the difference between a regular counter and a high-speed counter?
Counts pulses.
Well, one of them is supported by software, one of them is supported by hardware.
Oh, yeah.
So which one would be? So
Software micro.
software is programs. One of the big advantage, this is why digital logic is still out there. There's nothing I can do in digital using ICs that I can't do with programs. Nothing. So why don't we replace everything with programs? So even now, if I look at if I tear my phone apart, there's going to be there's going to be the processor, but there's still going to be all these dang integrated circuits in there. Usually there's two, right? So what advantage does supporting it with hardware have over supporting software? Yeah, hardware is faster. Hardware will always be faster, or has the ability to be faster. Because instead of me writing a program that a processor's got to run, right, you understand, that has to be so many lines of code. I would like to know actually how many lines of code a timer takes. Now we draw a little block up there, but you got to understand when you put that little block in there, it's got to develop a machine language programs of ones and zeros that tells the processor how to use a timer. So it's real easy for us because we're programming in a high-level language, but every time you insert a timer, what it does in the machine language program is it puts a program in there or a subroutine that does what? Handles the timer. So it might be 500-600 lines of code, not rungs, lines of code. So, and then that depends now on how fast the processor runs. So that's why we want these extremely high processors, so we can run those modules real fast, right? You understand? In the old days, when we first started writing games, they depend on the speed of the processors to run the game. And what happened was when they started upgrading the motherboards, you couldn't play your games anymore because they ran too fast. So originally they had what they called, where you could actually deliberately slow the speed of the motherboard down so you could still play your games. Eventually, they decided to start timing off interrupts. Interrupts are set by a clock, right? And the bus clocks for these computers, ever since, as long as, well, it's not true. The bus is running 166 megahertz. So no matter how fast your microprocessor is running internally, if I time off that 166 megahertz when I play my games, then even if I go to a new motherboard or what, everything's still what? That would be awful on my phone. If I upgraded my phone and now my games play too fast for me to play, right? You understand? So they got to be using something besides the speed of the processor to determine how fast these programs run. Normally we use interrupt. But what's nice about an interrupt is that, let me get to my thing. Y'all take a break. Let's bring up the slide. Allen Bradley supports two types of interrupts. One they call a timed interrupt. What do you think that means? Yeah, we use the timer, the timing register, and we have it come back and check that after a time, right? Does that make sense? So now we're not dependent on the scan time. So I might want to update something every minute. Well, instead of me trying to do that with a timer, I could do what? I could set up a timer, a timed interrupt that occurs every what? Minute. And then it goes out and every minute it would go out and run that subroutine.
But is that done through the scan?
No, it's done with the clock, the thing that's actually timing the PLC.
Yeah, I remember, yeah, the clock.
Yeah, that what, the S4 register.
Right, yeah, that's what I'm talking about, yeah.
And that's what it's doing. It's running right off that thing.
Right off that.
So what it would do is that every count or a certain number, it would automatically do generate an interrupt. It would go out and run it's a subroutine, but we called it an interrupt service routine.
Service.
So what would an interrupt service routine be? It would be a routine that takes care of an interrupt. Oh yeah, they are. That's it. That would be a selectable time interrupt. That's what the book calls it. What page is that on?
Interrupt the service routine.
Yeah, that's the program that's written, or the ladder diagram that's written to take. Y'all got to understand
Yeah, well,
Oh, thank you. That was the J. No wonder I can't find it. Because it's, so we have an INT instruction which identifies it as a what?
Interrupt.
Interrupt. Two main types of interrupts in Allen Bradley. We have what we call a selectable time interrupt, STI, and then we have an ISR, which is a what? Yeah. So what would an IO interrupt would be? Well, that would be me coming over here and pressing a button. And it don't even look at the scan cycle. It's going to generate an interrupt. And it would go out there and service that button when? As soon as the interrupt's true. And we learned to do these a long time ago. So now we can depend on something that's the same, right? We can depend on raising your hand if you got a question. So scanning would be exactly what I was talking about, where I would come up here and I would do what? I'd go one person at a time in the input. That'd be like scanning my input. And then after I'm through with that, I would update or say something or lecture depending on those questions. And then I would do what? Then I would scan it again. The interrupts would be like you doing what? Of course, what do y'all usually do when you have a question? We're not formal. You just answer that. So that would, but I stop at the time and take care of that. So that's an interrupt. Now, but we got a formal. So all we got is we got a timer interrupt. But this interrupt is just doing what? At a certain time. And then I have an IO interrupt, which is going to occur when you do what? When you generate an input, right? That makes sense. So interrupts are hardware supported. You know that, and of course, hardware means what's hardware?
Wiring.
That wired are physical parts of the computer. Not available on all Allen Bradley PLCs. I just looked in. We'll see if they're on the 504s. Anybody on the 504s? All you got to do is look at your instruction set on the top and see if these interrupts are available. I know they're not available on the 1000 because I just brought up RS Logic with 1000. So not available on all PLCs. Automatically generates an interrupt at a set time. These are selectable time interrupts. Used to force scans of high priority runs at a what? Set time. Third one there. Configured using the STI tab in the S2 processor register.
You gotta have a specific Oh, my.
Not to use the timed or the what?
The ISR, but I was sick from design. You cannot use a standard discrete IO module to accomplish an IO error.
Yeah, well, we're still in the STI, but you're right. So this is STI. So all you gotta do here, this is generated internal to the PLC. Y'all understand that? So you don't have to have a special module to do the STI, but your processor's got to support that instruction, right? You understand? Now Kathy was reading something that we ain't got to yet, and that's the IO interrupt. Well, the IO interrupt's got to be a special input because there's a line on the microprocessor or the processor called INT, which is interrupt. I'm sorry, it's called IRQ. Yeah. And so that means there is actually a hardware pin on the processor that supports hardware interrupts. Well, standard I/O modules are not connected to that because we don't want a standard I/O module to generate an interrupt, right? You understand? So what the book says is that to support I/O interrupts, you've got to have a special interrupt. They said module that actually supports that IRQ or that IRQ line. Well, right now let's get to well, I was answering the question I said. So what we're doing here is we're talking about selectable time interrupt. What we have is instead of like a JSR or instead of a jump instruction, we use an STI instruction. Right? Understand that? Everybody okay? But something we're going to configure, it says time between interrupts. So in the status register, the S4 register. By the way, S4, you don't have to specify S4 because if you specify S, it's going to use the status register. Right? You understand? So S40, this is the time between interrupts. Then S31, interrupt file number may be fixed at number 5. So this depends on the. So if I support timed interrupts, that's something you got to determine by your Allen Bradley PLC. So that means right here, if it supports this, you might have to use ladder 5, right? You understand, to support your timed interrupt. That makes sense.
/5.
Yeah.
It'll be S31/5, right? That's cold.
No, S code 31 contains the number of the interrupted thing. Okay, that makes sense?
Yeah. But what 5 come in? It's 5 on 5.
So you wouldn't use, if it's a file number, if it contains a number, odds are I will look at this, and that's a good question. It might be a dot instead of a
Instead of 5. Yeah, because if the slash is a bit, so it got to be a dot.
interrupt must begin with the what?
INT.
Right.
And
So it
that's
should
what
be in the
you'll
file
find
miscellaneous. So that's what we were looking at. And unfortunately, I need to see if I've got a. We can't. Can we open it? So this is RS Logics, and I'm sorry, this is Logic Pro. Oh, here it is. Okay, now. So this is 500. This is Logic Pro 500. I mean Logic, RS Logic. And when we go over here, and this is the problem we have with this, and we need to check the 504s to see if it supports that. So see when we go to miscellaneous file. Yeah. This is the MicroLogic. Let me put another rung in. There we go. Wouldn't pull down. I don't see it don't have an STI though. So STI is the software interrupt. And the INT is probably hardware.
What is that? So right there, what is the last one in that line? It's got a little tick to the right, all the way to, come over a little bit right there.
I don't know. We'd have to look that up. This is pulse width modulation. This is PTO, which is time something. I think it's a one shot.
Okay, right there, what is that? Will it shift or move?
User interrupt enable.
Okay, that's okay.
I'll try to show y'all pulse width modulation. Pulse width modulation is the method we use to control DC motors. It's really neat. Also, variable frequency drives use variable speed. AC drives use pulse width modulation. So this is considered to be an input instruction, and this is an IO interrupt. So we probably need to figure out which IO port is used. Since this is the, well, I don't even know which CPU they have selected. Oh, this is the one that's running mine, right? So this is the 1100 PLC. So this is the 1100 PLC that I've got up here. No, this is 1100.
Oh.
No, the program, the 500 supports all these commands in the book. So this book is written around RS Logic 500, which is not a PLC, it's a programming language, right? You understand that? It supports all these commands. But what depends on the commands you get?
The memory and the PLC.
Well, the PLC or the processor. Usually the memory determines on how many different things you could have. The processor or the operating system that you're running under, and that's what you're doing when you set up RS Logic, and you choose first thing you do is choose a processor, and then if it's a modular PLC, the next thing you have to do is choose what type of modules you have, right? You understand that? Fixed PLCs, normally you don't have to do that because the 1100 is a little different in that it is a hybrid PLC, which means what? Yeah, it's got this little slot on the side. We can open up that, and we could add modules to this, which is pretty neat. This is very, very popular now. These hybrid PLCs like this. I think.
Are we gonna do any hardware in here?
If we get somebody that gets ahead, normally what we do is we let a group to come up and actually wire this. But and you're more than welcome if you want to, but you'd have to set your program up for the 1100. And we could look at the information on the side. And sure, if you want to do that for one of your labs, you could not only write the program, but you could do what? Wire it up, which is real. It's not as hard as you think it is. It just looks complicated because there's so many ports on there that you're looking at. So is that okay? So what does it look like it's looking for now? So INT jumps an output. So odds are we'll have to somehow we're going to have to specify where the subroutine's at. So that's what we're looking to see. So odds are this guy right here is going to be the subroutine. And we'll see if it's a standard subroutine or not. Does that make sense? But it's looking for something over here. So let's see if the book tells us what we're looking for. This guy here does not look like it supports the
STI.
Yeah, let's see. Maybe it might be called something different. Let's put another.
But it's got the IO in there, so ain't the IO part of the STI?
No, STI is a.
Oh, the ISR.
Yeah. So we have two. We have what we call an STI. This is a what? This is a timed interrupt. And then we have the IO, which means this is going to be done by a. Yeah. So they're just calling it something different.
STS.
Yeah, so 1100 calls it STS. This is the selectable time start time. This would be the start time. So this is where you're setting up those registers. So this is an output, but I don't see the STI.
So is that automatically reset?
Don't know. That's a good question. I mean, I know how interrupts work in microprocessors, but I've never used it. In fact, why we haven't used it is the PLCs that we had down there didn't support this. So now that we got the 1100 PLCs, what was that?
You can do it.
Exactly right. So this is the STI. This is the selectable time start time. So this is an output. Let's see what else we got up here. Now I don't have a size idea whether. So this is scalar.
That's it.
You know.
You can.
I know what PTIO is.
PID.
This is the interrupt enable. Which the guy doesn't even talk about. It looks like it's an output instruction too. It wouldn't let me put it over there. Normally we have two types of interrupts on a processor. We have what we call an uninterruptible interrupt, non-maskable interrupt. And these guys are used for extremely high priority applications. So like when you press the reset button on the front of your computer or the off button. And then we have what we call a maskable interrupt, which means you can turn them on and turn them off. And that's probably what they give us available for right here. Keep going back, guys. So this guy right here, this little dash is this is an interrupt enable, so it's considered to be an output instruction. Oh, let's see what goes this way. Oh, yeah, we got some. I think we'll look at these, but I don't see a timed interrupt, do y'all? I mean, it's got to be in there. Why does it got to be in there? Because we got a selectable time, start time. So I'll see if I can look up the instruction set and see exactly where it is on the 1100 PLC. I know what PID, I know what proportional, and the 1100's also got a analog, inputs on it. So we probably got a command in here where we can play around with analog.
Do you know the instruction we used to have it and toggles back and forth? I'm trying to think of it. We used to have like green lights that toggle back and forth. Sometimes they'll stop. We used to have to go in there and reset them sometimes.
I didn't know, yeah, there is. We'll see if it's covered later on the book. They do have a toggle instruction. It's in there. I mean, that's a good point. I just don't remember where I saw that. When you toggle something, what do you think that means?
Change it from one state to the other.
Yeah, you just flip it. And it's in here. It's supported by this. I just don't know where it's at. Guys, I don't see on this, this is the 1100 PLC, the MicroLogic 1100, and I don't see the time, huh?
There's nothing on Logic Pro.
No, Logic Pro don't have any miscellaneous. They don't have any trig function. The 1100,
You're on Logic Pro, man.
What's that little genie on that for?
Oh.
The little man on that.
It's a wizard.
he's a wizard.
What are you on that for?
He just right click on him and say hide.
And
He
you
in the
get
way.
something wrong, you take it too long, boy.
Oh yeah, he goes to sleep.
Man.
Okay.
I turned him off. Yeah.
I wonder why you there.
Making me sick. Shut up, man.
Yeah, y'all can just right click on them and say, so this guy, even the 1100 doesn't, a Micrologic 1100 doesn't support any, it's got some absolute values and, encoder and decoder, functions, swap bytes, and then, scale. But, as far as going to trig functions, it doesn't support trig functions. So, the book doesn't cover it.
5,000.
Yeah, we got a 5000 down there. It's in a box and we never opened it.
5,000 do it all.
Yeah, but we look at the difference in the price between what you're doing when you get a PLC. You don't want to buy stuff. It's like people that buy smartphones, right? And they spend all that money. And they don't ever use anything. They just play solitaire on it, or go to my Facebook or Twitter or something like that. And yet you go out there and you pay all this money for something just to say you got it, right? So this is what we call enable and disable. So we got a STD, which is going to do what? What's the matter?
Come on, Rick. You got an STD.
So,
How you
y'all still got me here.
how you stop getting STD?
DD.
Oh, I know. So I went from this, it was over my head. to
Yeah,
here.
we're right.
Guys, I can't do anything about that. Selectable time interrupt disable. So if there's sections of our program that we don't need, that we can interrupt, right? You understand? Very, very important sections that we don't want this thing to interrupt. What can we do? We can do what? We can disable it before, right? We can disable it.
I'm sorry.
Well, I know a story just popped in my head, I can tell. Selectable time minute, but it was fun. Remember, I was in the Navy, so yeah.
Change the name to protect it.
Yeah, right. So, it was above my head, but finally I caught on. Then what we would do is, once we got out of that section, we would have to make sure we did what? So these interrupts, we have the ability to do what with them? Enable them and disable. Does that make sense?
Is there anything you can't disable?
Anything what?
That you
That maskable interrupt you can't get rid of, but I wouldn't think they would make that guy available to us. Those are really, really high priority interrupts, and they're called not, so this is what in processors, that's what we talk about. We talk about maskable and unmaskable. So an unmaskable cannot be ignored. So what would happen when I have a maskable, it means it's a formal classroom, right? You understand? And if you raise your hand, I'm gonna honor you, but if I mask it off, I just do what?
Keep right on track.
And then you're raising your hand out there, and I'm gonna keep trucking, because right now I'm doing something very important. It's just like even now, you might raise your hand, but if I'm in the middle of an important sentence, or I go ahead and do what? So that's what I'm doing. I'm literally just masking you off. Now eventually I'll do what? I'll enable it, and I'll come back and answer your question. You can understand, because if I stop mid-word, didn't finish a word or didn't finish a sentence, then it would be more confusing than, of course, I do that sometimes.
So you said a maskable interrupt cannot be disabled?
No, it can. That unmaskable guy, we call him in technical. So if you ever looked at the pin out of a microprocessor, you're going to have two pins. One of them's going to be called IRQ, and one of them's going to be called NMI. NMI is non-maskable. And they don't use that thing all the time, because that means the processor will not ignore that value. The IRQ, though, which is the maskable interrupt, that means I can do what? Yeah, in the old days, they used interrupts to keep up with the time on a computer. So they would generate an interrupt, like every second, and then it would go out and run the little program out there to make the clock on the bottom of your computer change time. This is before we had a lot of what we call multitasking, which means the processor could only run one program, period. You could only have one program in memory at the same time. So what would happen is the clocks on your computer would always get off. Why? Because when they was running something very important, they'd mask that sucker off all the time. I don't know if you remember the old computers, you had to reset the time on all the time. Now we don't do that much because they load in a background program that's the wall. And sometimes they can still kick that out too.
Hey, since you was talking about computers, and computers have like what, dual processors, right? Some of them.
Well, yes and no. We used to call them, in the old days, we had what we call multi-processor motherboards, and you literally had more than one microprocessor on the motherboard. Then they went to what they call multi-core processors,
Right.
where they put multiple cores inside the same unit, which means we have the ability to run different threads, but we still share stuff inside the processor. So like your cache memories and stuff like that are still shared. So they don't run as fast as multi-processors, but it saves a lot of money to be able to support those.
So it's actually not two processors, it's just one.
It's still one processor running multiple cores, which means each one of them's got their own math units, each one. And what we do is, there's a difference between multitasking. Multitasking, what you do is you share processor time between the processors. So that means the more tasks you have open, the slower everything runs because you're time sharing. Multi-thread means that the program is written in modules. And what you do when you load the programming in, it assigns a different module to a different core. Yeah, so we call these multi-threaded applications. And those guys scream if they're written correctly. But still a multi-threaded application, and you load in two applications, then you're not doing multi-threading, you're doing multitasking. So it's just like you when you multitask, you don't do two things at the same time. So, go learn a little bit about processors. Believe me, I've come up through it. I know a lot about microprocessors. If you got any questions about microprocessors, just ask. So this is showing us, this is the SL504, so the 504 must support this thing. And they're showing us the status register, the S2 register, and what do we have here?
The S30.
The S30, which is the set point
That's 31.
in milliseconds, okay, or tens of milliseconds. And then we would put the file number in S:31, so it's a 16-bit register, right? On these registers, if we don't specify a word, then it's going to assume a word, right? Y'all understand what we're saying? So of course, inside our counter, we have to specify a word. But if I'm specifying a register, if I just put S:0, it's going to use the one. So the set point is an S. In fact, this is actually right out of the process right now. Is this in your book? I mean, yeah. So these were actually cut and pasted directly out of the processor for the 500 SOC.
No.
I don't think that's enough.
504. Yeah, it's not in your book. What I said is I brought up RS Logics and I connected to the 500 PLC. And so the book says, okay, this is the register they are. What I wanted to actually show you is what it actually looks like on RS Logic, right? Yeah, so this is directly out. This is the MicroLogic 1000. Okay. Here's the S30 register. The S30, S:30. Y'all see that? Yep. And then this, what is the 30? What is the 30 register hold? This is the time, how often the interrupt was. occurs. And I don't see, what's the other one, 31?
Something off.
Yeah. So it looks like the Micrologic 1000 automatically uses what? Yeah, so the Micrologic 1000 supports timed interrupts, but you don't have to specify the file number. It's gonna use what? 5. The 504, you come up here and you specify the time in S30, right? 30. And then you specify the file number in what? 31.
Hey,
I don't think either one of these supports, so go ahead.
can we see what's in that scan time file?
We would have to be online. I can put the, of course I've screwed this up. So what I'm gonna do is I'm going to, golly, I don't know where it's at, guys. So let me just, I'm not gonna save this. What I'll do is I'll just load it up again. And what we need to do is to see these things changing, of course, is it needs to be in the run mode, right? Okay, I need to come back down here. This is it. Y'all know how much I love
How you keep over all this?
the Screencast-O-Matic. So it's running right now. It don't even show up anymore. So what we'll do is we'll connect to this PLC right here. Make sure we're active. So there it is. I need to figure out where it's putting these at. And so here we go. Okay, so what we're going to do is, what do you want to look at, Vincent?
The scan on the S file.
Okay, so this would be the status, right? We bring that up. We're not in run. Wait a second. So let's switch to run. So here's the S4. It's actually S2 colon 4, but like I said, you don't have to specify the 2 when you go to the status. And here's, that's the processor information. Here's the scan time. Here's our math. This is where our overflow, our 0 bits, our sign bits, our carry bits. So this is inside the S2. Okay. This is where we go, by the way, to see what type of errors you have. So right now we got a couple of PLCs that's faulty. So what we would do is we can connect to them. You can't connect to them through. If you can connect to them, you can bring up the status register, look at the status, and look up the error code and figure out. And, you can look at these up on the internet, and they will tell you. Sometimes you feel like a nut.
So the fault code's not listed within the PLC itself?
What's that?
The fault code.
They are listed within the PLC, but how do you get to them?
Search for the file.
Well, what you do is you go in and you're gonna go to what? Go to errors.
They have to go to the back.
Yeah, and over here, the error code would be over here on the right.
Fault machine.
Major errors. What we're looking for is everything's okay. We're looking for what?
Low.
No,
The fault
zero.
would be a high, right?
Everything
It'll
low.
be a 1. It says we're looking if everything's okay.
Oh, is everything okay? It's good. Yeah, it's all 0.
Now we need to. Oops.
The scan time is the internal clock, right?
No, that would be the time it takes to scan your
Program.
whatever program you have in memory. Not on the actual PLC, it's adjustable on Logic Pro. Because the problem with Logic Pro is your scan time depends on the speed of your computer, not on the speed of the PLC. So on your actual PLC, you cannot play around with the scan time. The problem with Logic Pro is that, like on my computer at home, it's a screamer. I put them on my laptop, everything's different. But what I can do is I can play around with that scan time on Logic Pro and make them appear to be the same.
Watchdog.
By the way, once you bring this up, all your registers are available. Y'all see this right here. So there's the bit register. There's your timer registers. There's your counter registers. Can y'all see what I'm doing? There's the control registers. There's my integer registers. There's my floating point registers. This processor supports B10.
And pretty good.
So, okay. So that what you want to say, Beth?